In high-stakes environments such as operating rooms, surgeons often need to shift their attention to access critical information like neuromonitoring data or CT scans. To minimize these distractions, one approach is to project this information directly next to the surgical site. However, current state-of-the-art systems do not account for shadowing when dynamically projecting onto uneven surfaces. To address this limitation, we propose a multi-projector setup that projects onto the same surface. Still, even with highly accurate surface reconstruction and geometric correction methods, dynamic multi-projector systems face small inaccuracies. These minor misalignments can lead to subtle blurring in the final image. To combat this, we introduce a blur mitigation pipeline that computes shadow masks for each projector and uses distance transforms to assign each region exclusively to the projector with the greatest distance from shadows. This approach also helps compensate for sensor latency. In a controlled user study using simulated shadows from a virtual occluder, we compared two blur mitigation strategies, a per pixel assignment and a tile-based assignment. For a fair comparison, the baseline condition also included shadows, but no blur mitigation. In the per pixel method, each pixel is individually assigned based on the greatest distance from shadows. In contrast, the tile-based approach assigns entire GUI tiles to a single projector. Blending between projectors occurs only at the tile level when a projector reassignment occurs. Compared to the baseline, both approaches significantly reduced cognitive load and improved the readability of texts and plots. During development, we observed strong environment-dependent multipath interference effects when using the Orbeck femto-bolt sensor, whose time-of-flight sensor is technically identical to that of the Microsoft Azure Kinect. In contrast, structured light sensors despite their lower frame rates avoided these issues. Using our adapted point cloud rendering for geometric correction, we achieved an average error of just 1.6 millimeters, even on highly uneven surfaces. With our precise geometric correction and blur mitigation approach, we present a projection system that significantly reduces shadow artifacts while maintaining high image sharpness. Our techniques enable an interactive projection system for dynamically uneven surfaces that supports gesture-based input and head tracking for intuitive user interaction.